Hi everyone, I'm Steven and I'll be presenting on behalf of the Transitive Inference team on our work in abstract relational knowledge in ANNs for transfer learning. And this is joint work with Alisa, Shilai, and Zeynab. So starting off with the motivation, relational learning is a hallmark of intelligence. Humans are quite good at learning and manipulating relational structure for a variety of domains, including spatial, numerical order, and linguistic syntax. And this capability is intimately related to our ability to abstract, being able to recognize and then learn and apply learned abstractions to new settings likely underpins our ability to solve various problems. So we're after two questions in this work. One, we want to verify whether we can find interpretable structure in networks. And two, we want to understand whether this learned structure can actually improve learning for downstream tasks. And we focus on studying classical cognitive tasks. So to go over the tasks, TI, transitive inference, we first assign a linear order across a set of stimuli. So in our experiments, we used 8 items. The encoding we used was random orthonormal vectors, so they're maximally different. Sometimes I might say a semanticless. And during training, we feed in adjacent pairs to a feed-forward network, and we output one, say if the left item is greater than the right item. And by adjacent, I mean that the two pairs are next to each other when they've been sorted. And during tests, we measure performance on all non-adjacent pairs. So this is standard in the TI literature. And for the downstream sorting task, we have the RNN take as input pairs again, just as in TI, for a total of six pairs per data sample. So if we look at the bottom diagram here, it's just to give some intuition about what the task looks like. So we can see that for at time step 0, we get the pair 1, 9. And because the input is already sorted, then the output just needs to be 1, 9 with the rest padded zeros. And at time step 1, say we get 1, 7 or 7, 1, and the network needs to output the sorted sequence of all the numbers it's currently seen. So it needs to output 1, 1, 7, 9, and the rest zeros, and so on. And so to assess task transfer, we want to use the trained encoder that was used for TI. And we also used various other encoders for comparison. And so in total, we use 5 different ones. 3 of them have different kinds of pre-training, which I'll discuss in the next slide. And the 2 of them were randomly initialized. One of them had weights that were kept frozen, and the other one was trainable. And here are the results for TI. So we found that the latent space of the encoder does indeed encode the rank. So at the bottom left, you can see this nice picture of all the different stimuli sorted by their rank. But interestingly, we only found this for a specific tweak in the feed-forward network architecture. So instead of having the input being a pair of items, we had the encoder process each item individually. And if we had it the other way around, where the network was processing the entire pair at once, then we weren't able to find this latent encoding in very nicely in the space, but it was still able to solve the problem. And for the downstream task, the model using the fully pre-trained encoder on TI, so that's the high quality line in the graph, actually converged the fastest, even faster than the model that was used, than the model with an encoder that was pre-trained on the sorting task itself. And that one is the dark gray line. And so performance here, most of the models actually got 100% performance. We were really measuring the convergence speed. So for the 5 different models, higher quality means that the encoder was the TI encoder was trained all the way. Lower quality means that it was we had some early stopping, only going like maybe 50 epochs instead of 100. And as I mentioned before, there were the two randomly initialized encoders, and then we had one more encoder that was pre-trained on the sorting task. We also had another set of tasks, which I'll call the ordinal task. So task one is really similar to TI, but instead we're using random pairs of integers. And for task two, it's a little bit more complex. So now we have the network sees a sequence of 5 integers, and it needs to output 1 if the number at position 2 remains in place if the sequence were to be sorted. So it has to do sort of like an implicit sort. And task 3 just combines task 1 and task 2, and we consider two different scenarios. So first which I'll call MT1, we train on task 1 first, and then fine tune for a few epochs on task 2. And then similarly, we reverse that, and I'll call that MT2. We train on task 2 first, and then fine tune for a few epochs on task 1. And here are the results. So we found that MT2 had much less catastrophic forgetting compared to MT1. And so you can see for MT2, if we were trained for task 2, training before fine tuning on task 1, we got 83%. And then after fine tuning, it only dipped a little bit to 82% versus the dip between 99% and 61%. So the reason for this is because task 2 is much more complex. By the time it had to perform task 1, it had already learned a lot of structure. So there was very, very little forgetting, and so it can reuse that structure for that task. Alrighty, so that concludes our work. We investigated the formation and the transfer of relational representations for very small neural networks. We found that both set of tasks exhibited pretty successful transfer, which underscores the potential for abstract relational representations to serve as a foundation for transfer learning. And of course, we want to say thanks and acknowledge our mentor, Moein, for all his time and for all the great feedback he gave us during his sessions, and for Sam Lipple for his mentorship for Alisa during our time. Thanks so much.